I hope all of you are doing well today. I am Mr. Ish. Thank you for joining me. I'm showing you here a unique derivation perspective for a volume of a regular triangular pyramid. I've presented this subject before, but here we're doing a unique sine theta perspective. In the previous videos with regards to the regular triangular pyramid volume, I've shown you something like this. Volume is equal to 1 over 3 base times height, where that b is a capital. But I've also shown you this other formula. And this formula is b squared h over 4 root 3. Here you're dealing with sides, b, lowercase b, and height. And here you're dealing with the capital B. That capital B here would be the area of this base times the height times 1 over 3. Either of these formulas for the volume of a regular triangular pyramid are good. And they're unique in their own right. Here I'm showing you something totally different. The end result is still the same in terms of what we have for a volume of a pyramid, but we are doing a sine theta perspective. I'll include the tags for videos associated with these formulas, so I won't have to talk about them in this video. How does this sine theta perspective come into play? Consider this. You know, for area of a triangle, it's always half base and height. And if this were to represent a triangle, this here is my base, this here is my height. You know, half base times height is a area for triangle. But if I were to bring a theta here and a hypotenuse, a right triangle here, I can do sine theta is equal to height over a, the hypotenuse opposite over hypotenuse, and h is equal to a sine theta. If I were to take this h substitution and put it right here, I would have a half base times a sine theta. This is another formula for the area of a triangle, a geometric formula which brings in a sine. You know this, you've seen this. Now imagine if you have a equilateral triangle where you would expect it for a regular triangular pyramid, all of these cross-sectional slices would be equilateral triangles, equal sides. Then you can imagine this a and this b would be the same, and you'd have something like a b squared sine theta over 2, because the a and the b are equal. And this right here would be equal to hypotenuse for an equilateral triangle, so ab sine theta over 2 can become b squared sine theta over 2. Keep all of this in mind. Everything is coming here with regards to this representation of an area for triangle. So how does everything play out for this unique sine theta perspective? It plays out in this way. You have a certain side of this equilateral triangle. Everything is coming based off a certain ratio. You know, the pyramid is broad at its base and it converges towards the top. You have a complete height of a triangular pyramid. You have a complete base. And I'm looking at everything here in terms of vertical cross sections. And you have a partial height and then you have a partial base. This is what you're solving for, because this ratio will give you the ratio of convergence from the base to the top. X over s, small over small, is equal to full over full in terms of heights and base. You solve for s. S is equal to xb over h. This right here plays very well. My triangle, equilateral triangle slice is made up of S, 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 because these are equal sides. They're 60 degrees, and you cut it across here, 30, 30, and 90. You know, I've already told you area for triangle is considered to be half AB sine theta, but it's also equal to half base and height. For here, if supposedly all the sides are represented by S, area is equal to half S, S sine theta, where S is equal to an A, S is equal to B, because we have equilateral triangle. Everything here is in terms the same side, S square sine theta over 2. But I know S is equal to XB over H. Bring that over here. Area of each cross-sectional slice is equal to half XB over H. There are two of these sides. You see an S square, I'm bringing in S square sine theta. You know what the basic premise here is. You're taking a cross-sectional slice, you're going to integrate the area of the cross-sectional slice from a lower limit 0 up to an upper limit h, and you'll get your volume. That's the basic premise, integrating an area across a limit. This right here is my area. But sine theta is not a unique variable here by any means. It's a trigonometric ratio. Sine theta here for an equilateral triangle, which is a slice of this type of pyramid, is equal to sine of 60 degrees. Trigonometric ratio is equal to root 3 over 2. Once you've figured that out, you bring root 3 over 2 right here into place of sine theta, and now suddenly you have a good expression. Consolidate all of this. You have a root 3 over 4 x square b square over h square, which represents the area of each cross-sectional slice. That will integrate from a lower limit 0 to an upper limit h. dx, it doesn't have to be dy. This pyramid could have been tilted horizontally, then you're looking across. So all of this is good. Dx, dy, doesn't matter. Your orientation could be easily in this direction and you're good. Bring everything out except for the x. Bring out all the constants. You have a root 3 b square over 4 h square 0 to h x square dx. Integrate this. The antiderivative is x cube over 3, upper limit h and a 0. What do you have here? H cube over 3. This h cube over 3 is multiplying with all of this. And when you do that, you will have here a root 3 b square over 4h square times h cube over 3. Simplified. This h square will cancel out with this cube. This root 3 here will convert this lower denominator 3 into a root 3. You'll essentially have a b square h over 4 root 3, which is exactly what you see right here, a very legitimate formula. When you integrate all of this, you'll have the volume, and that will be equal to b square h over 4 root 3. Everything here coming from a unique sine theta perspective, as you see from right here and this right here. Again, remember, sine theta was equal to sine of this angle, which by means of trigonometric ratios is root 3 over 2. And that came into the picture right over here. But that's what I'm showing you here in this video, a unique sine theta perspective for the volume of a regular triangular pyramid. Have a good night. Bye.